Thank you for inviting me to give this talk. I'll describe the tau performance system, another open source performance evaluation tool that allows you to look at the performance of your application on both CPU as well as GPU systems. And for those who are impatient, I have a quick start guide that gets you started. Okay. As you will see here, all you really need to do is have an uninstrumented binary, and without any changes to the code, you can just simply launch it with a tool called tau exec, passing in different parameters for different cases. And you can generate performance data and view it. Okay, that's if you want to install it on your own laptop, these are the steps. So the key problem that we are facing is that as our frameworks get more and more complex, it's getting harder and harder to measure the performance of your applications. Also, it's getting harder to install all our tools in a consistent software stack. So to address those problems, our first tool is the tau performance system that aims to deliver a scalable, portable performance evaluation toolkit. And the second part of this talk includes how to install all our tools that you heard about in the morning. You heard from vendors, Intel, AMD, NVIDIA, they all presented their tools. Well, their full runtime systems, their complete compilers, MPI, their software stack, along with our tools, including open source tools like HPC Toolkit and Tau, can be easily installed using what is known as the Extreme Scale Scientific Software Stack, or E4S. And I'll try to cover quite a bit, but there is a lot of material in these slides, and I'm not going to cover all the slides. I just want to focus on the key parts. With Tau, you have three parts to this tool: instrumentation, that is adding probes to your code; measurement of generating profiles, traces; and then visualization or analysis of that data. Okay, and we can do this in many different ways. The important thing to take away from this talk, and I know you're getting a lot of information today, is that you can take your unmodified binary and simply launch it with a Tau tool, collect the data, and you can dial up or down the amount of data that you want to collect using some environment variables, and then launch the viewers for profiling and tracing. If there is one takeaway from this talk, it should be just that you can easily instrument your code by just simply loading a Tau module, changing the command line. You can do all the analysis even with command line tools, or have GUI tools installed locally or remotely. And we do instrumentation in many different languages, automatic instrumentation in all of these. But you also heard about things like NVTX, where you can add your own start-stop statements in your code. You can do the same thing with RockTX from AMD. There are other frameworks. You may have frameworks like PETSC that you're using, or Cocos, or some other framework which is using CAM timers library, or some interesting way to annotate your code which says start a timer here and stop it right here. Those timers can flow into Tau automatically. So all that instrumentation knowledge that you already have in the framework can simply be redirected to map onto the Tau calls, and I'll give you examples of those. There are frameworks like Caliper, which are very useful for instrumenting your code too. And we already have such instrumentation in our frameworks, and we'll just reuse that. And we support a number of runtimes, MPI, OpenSHMEM, all the way to threading systems with OpenMP. We heard about OpenMP target offload directives. Tau is shipping with support for those, so you can see exactly what's going on the CPU, what's going on the GPU with OpenMP, OMPT calls. We have support for GPU runtimes, Intel One API, DPC++ SYCL, AMD ROCm with Rock Profiler as well as Rock Tracer, CUDA using CUPTI, OpenCL, OpenACC, Cocos, and we have a number of analysis tools that I'll describe. But you are probably wondering, what can Tau show me? Right? Tau can show you where the application is spending its time, at which function, at which loop, at which file, you can see what happens on the GPU's kernels. You can measure them precisely. You can see the data transfer between the CPU and the GPU. You can see how many instructions were executed. You can measure using the PAPI, hardware performance counter, or Liquid. These are two important tools, and Tau supports both of them. So you can measure floating point instructions, branches taken, all of those low-level hardware performance counters. You can see how much time was spent waiting in a collective operation. You may look at the full trace and realize that the GPU execution was very tiny. Most of the time was just spent in MPI collective operations. And how much of that time was spent at a barrier within a collective operation waiting because one of the processes didn't make it to the collective operation in time. You can measure precisely what was the MPI sync wait time in a collective operation. You can measure the multi-node GPU executions. We heard about limitations with tools, even vendor tools, where they are not able to handle multi-node execution. You can measure it, and you can just launch the tool, and all the collation of the addresses to the source line numbers occurs online in parallel at the end of the execution. So as soon as the execution ends, you can just launch your browser and view the performance data for both profiles as well as traces. You can do that with, especially with the OTF2 tracing that we have support for. You can measure the memory usage, I/O usage, energy usage, even the scalability of your code. So there's a number of things that Tau can do. I'll just touch on some of them. And the basic important thing is, how do I add the hooks to your code? While it's possible to do entire source analysis with Tau, and we have frameworks to do that, the Program Database Toolkit with Tau provided compiler scripts, we can also do compiler-based instrumentation. We can even go deep inside the LLVM intermediate representation and say, I want to measure this or I don't want to measure this, have selective instrumentation at that level. But the most easy to use way is just to use runtime preloading with a tool called Tau exec. So all you need to do is, instead of app run a.out, you say app run Tau exec a.out, and then you get the data. Okay? There are some options that I'll describe. And what can you generate? You can generate profile files which tell you summary statistics. If a function is called 100 times, one line is written out at the end which says, this function MPI barrier was called 100 times, it spent 35 seconds in it. You can create traces which are event logs that show you timestamped log of events of what each process was doing at any point in time. Okay? So with the direct instrumentation, where you have start and stop timers, these probes can show you what happens in your code and generate inclusive and exclusive measurements. What do these look like? Well, if I have a function called foo, and it takes say 100 seconds, and it calls an instrumented function which has start-stop timers, and bar takes 30 seconds, then I'll say inclusive time of foo, this thing in green, is 100 seconds, and exclusive time is 70, the time spent outside of the bar function. And this is how it looks in a typical profile. It's inclusive time. It shows you a .tau application, which is the top level timer on any thread. Okay? And within that, you can see exclusive time, where a particular loop may be taking a lot of time. In this case, there is a solver loop, which is taking a lot of 43.6 seconds exclusive time. Okay? So that's the inclusive versus exclusive terminology. And with that, you can generate a number of different types of performance data, including call path profiles, call site profiles, all the way to traces. But the key important difference here is, either you have direct instrumentation with probes which have start and stop calls, like with a cam timers library or some your own Tau API, or you have indirect measurement with sampling, where you get a periodic interrupt. It interrupts your code, you see the program counter, it correlates it to the file and line number. And it works like this, event-based sampling. So wherever you see the word EBS, remember it just means your program is interrupted periodically. Here is an interrupt, here is another interrupt. It can happen between functions. So you may miss some things. It's like throwing darts on the board. But based on that information, you construct a profile and you say, I estimate that the time was spent over here. Similarly, with instrumentation, you have precise start and stop calls inserted in your code. These calls tell you that the function starts here, it stops over here. And with that, you can generate an instrumented file and then generate the performance data precisely. So you have a combination of sampling and direct instrumentation, and Tau supports both. So you can see that lightweight functions can introduce overheads, and especially if they are called frequently, but we have a way to throttle away those lightweight routines so that you can still see a meaningful profile. And we use the Tau exec tool. It can show you the time spent in the runtime calls, the calls in MPI, OpenMP, CUDA, Cocos, all of those libraries can be instrumented. Even your memory and I/O can be instrumented with just Tau exec with the right option. And the best part is you don't need to change anything in your source code, build system, or your binary. You just launch it with Tau exec and generate the performance data, and then you can launch pprof or paraprof. And this is how it looks. If I take an application and launch it with, say, srun or apprun with 256 cores or 256 MPI ranks, then I can say Tau exec with a tag, the -t, and specify a configuration of Tau, and then what option I want to measure. Is it ROCm? Is it level 0 for Intel GPUs? Is it kubectl? Is it OpenCL, OpenACC, or OpenMP tools interface, OMPT? These are just options that you can specify that turn on the hooks for this runtime. And then you can generate the performance data. You can say Tau exec -EBS, and that means turn on sampling. Tau sampling is turned to 1, and then you generate the profile file. Okay? So all you have to do is change your batch submission script. Typically, it involves saying module load Tau, and your apprun or srun command has a Tau exec with some options, and your application executable. You run it, generate the data, look at it with pprof, paraprof. And these tags that I mentioned, you see, when I configure Tau with a particular set of options, like use OpenMP tools interface with OMPT, with MPI, use the BFD package, download it, you use a package for PDT, PAPI, it creates a stub makefile, which includes where these compilers are located, where these packages are located, and it has these tags in its name, like makefile.tau with PAPI, with MPI, with OpenMP tools interface, one with MPI, one without MPI, one with OMPT, one with just pthread. So these tags are what you can refer to when you say Tau exec with the -t option. If by default you want to omit some tags, that's okay. It will find the shortest makefile name, and then it will just load the library in the shared directory which has the same tag names. There's a libtau.so there, it just preloads it. That's all Tau exec does. Okay? And if you don't have MPI, then please use the -t serial, that's all. So with this runtime preloading, you load the library, and then the application gets loaded, and then those calls of the application, the MPI calls, OpenMP calls, they just get intercepted with the preloaded library. So you must compile your code with -g and also -dynamic during linking, so you have an executable that's dynamic. And then you launch paraprof. This is our GUI tool, and you can see over here all the MPI ranks on the left side and the total time in different functions, color-coded functions. I can just stack the bars separately, and then each function has its own space, and you can see how much time was taken in each of those. And you can then look at different threads and see there's CUDA functions here in these threads, there's some OpenMP threads, and so on. And you can right click on the left side and then just turn on, explore which windows are there, like a thread statistics table on the third side. Okay, you can just look at that. And here, it will show you a top level function, the .tau application. It just is the top level routine. And all the MPI functions are listed below that. And you can see over here that if you expand this thread statistics table, in this case, it says that the inclusive time was 13.3 seconds. The exclusive time in your application outside of MPI calls was like 12.1. Now, if you expand it further, you will see a context. This is the sum of all the samples we collected. But sampling is imprecise. It cannot explain the full data. So it's saying that out of the 12.1 seconds, I can explain, the best I can do is I can explain 11.9. And that's close enough. So then you can look at the samples by expanding that, and then you will see that 11.9 seconds came from a function called grad h underscore, and then there was some unresolved symbols coming from a library called libc, there's a libcuda, and all of the other nodes over there. So you can expand the summary nodes, it will go down to the sample nodes, and you'll see the exact line number where the call came from. So you can see now that there's an exchange core.f90. At line 339, it spent 0.66 seconds. So you can go right down to the statement level, you can go down to the function level, you can look at the MPI data, you can look at the CUDA data with no change to your binary. Okay? You just said tau exec and launched it, and then you can get down to the statement level. You can look at Python codes, but instead of tau exec, we have a tool called tau Python. That's the only change. And so you just launch tau Python, and then you will be able to see detailed information about kernels executing on the GPU. You'll be able to see Python functions, and you'll see all the information in Python calls. So every Python entry and exit will be instrumented. If you just use tau underscore Python, it has the same set of arguments as tau exec. Then you can look at the inclusive, exclusive time, look at the summary of all the functions, MPI and the rest of your code, and even look at the source code and look at a context event window, which shows you the extent of variation. You can trigger an event with some data. What kind of data? Well, if you had a function that called a message communication primitive, so you're just sending a message, the size of the message can be encoded as this context event. It will show you where it was called from and what was the extent of variation, minimum, maximum. Here I'm looking at I/O, or bytes copied from host to device. And you can see what was the minimum bytes copied, what was the max, what was the standard deviation, mean, and so on. You can look at this in Python with MPI, even turn on sampling. And then you can also look at when a sample was taken, I can unwind the call stack and see where the program was when that sample was taken by just turning on environment variables like this. So here, I have introduced you to environment variables like export tau event-based sampling unwind equals 1. That will allow you to unwind the call stack. And then you'll be able to go all the way deep down into the system libraries. System libraries as in vendor libraries, where they have forgotten to strip those. And they have shipped it with all the debugging information. So you can see what was going on in the rest of your code, thanks to the vendors providing those libraries with the debugging symbols. In some cases, you will not find the symbols. libcuda.so does not have the symbols. But in many cases, you will find that they have shipped those libraries with those symbols on. And so event-based sampling or unwinding the call stack, you can even see the name of the person who compiled the library and the full name of the file. You can see the samples where they are taken with Python. Here is an example of the thread-by-thread execution of a kernel over here. You can see this with an uninstrumented code. You just said app run with tau exec with EBS. And then you'll be able to see at which line how much time was spent. With call side profiling, I can partition the time in a function based on where that function was called. If MPI receive was called in multiple places and it took 14.6 seconds, then if I turn on call site equals 1, I can see that the MPI receive, which was called from exchange 1 function at line number 68 in exchange 1.f, that accounted for 12.6 seconds. The other MPI receive calls at line 86, 113, they took much less, about 2 seconds. So you can see exactly which line in which code had how much impact. This is the interesting part, the collective sync. You run your application, and as you scale, you will see that collectives are taking up a lot of time. But they are not taking up a lot of time because the network is slow. It's because one of the MPI ranks has not reached that synchronization operation yet. So what is the time spent in an implicit barrier inside a collective operation? That time is MPI collective sync. And if you turn on the call site or the call path profiling, you can see exactly who called that. So here it's saying 574 seconds were wasted in this collective sync operation on this thread, rank number 118. And out of those 574 seconds, 382 came from the MPI all reduce operation. That's where it was stuck. And out of the 15,000 calls, 9,500 of those MPI all reduce calls accounted for the 382 seconds of wasted time. So it pinpoints to you right there saying this is where the MPI calls were wasting time. Fix this, make MPI collective sync go to 0. Then you can worry about the other things. Otherwise, you might be thinking that I need to tune this kernel on the GPU. And when you look at the profile, it will say MPI collective sync is taking 500 seconds. That GPU time is like 0.3 seconds. Okay? 500 seconds are wasted here. First fix this, then you fix all the other things with the GPU. And you might find that to be the case, especially as you scale your codes of how much time. And you'll see that there are other calls that the framework added itself with start-stop timers, and they were just mapped back to tau. So you can see where Cocos parallel for copy particles to device came from, and all of those timers. This is what I'm saying, that your application framework likely already has start-stop calls. Leverage that, let them be mapped to tau calls, and then you'll see all of those user annotations in a profile, just what you want to see. Not 20,000 functions, but just what the authors of that framework intended to annotate. And here you can see the comparison between multiple threads. Here is thread 22, MPI rank 22 versus 118. And you can see some collective solver information. You can see bytes written to a file, write bandwidth. You can also visualize this. This is the 3D browser of Paraprof. You can see MPI ranks along one axis. You can see the functions along the other. And then these crosshairs where they intersect, you can see the height and color. And here is the bar plot view of the 3D browser. Where these two lines intersect, you can see the function and thread and see the height and color value, the exclusive time. So you can zoom in, see the shape. You can see the shape of what the whole program was doing at once in a profile. You can also see the Paraprof topology window. Now this is very interesting. Here is a function, MPI all reduce, and you can see that when you asked for 512 MPI ranks, you didn't get them all contiguous in one nice location. There were some ranks here in the machine, some were over here, some were distributed. Where did my function actually execute? On which ranks? Where were these ranks mapped to the physical topology of the machine? That's an important question. You can see all of those in a cray, and with crays it can just collect the topology information, correlate the information, and then show you exactly where that function, MPI all reduce, was spending its time physically on the machine. So if you have bunch of nodes that you got in one allocation, which are not in the same nice rectangle, you'll be able to see where it was hot, red hot, versus where it was cold. And then you can see 3D communication matrix. And then let me just cover what we can do with GPUs. Now I know you are all interested in trying out Intel Dev Cloud, and they have various generations of Intel GPUs. We can use level 0 to take an unmodified binary and then launch it with tau, and you can see all the kernel names and how much time was spent in each kernel. You can see all the time spent in the level 0 calls on the left side by just saying tau exec with -L0. Okay? And then you can measure multi-node performance with tau, launching it with MPI run or srun or app run. Here is an Intel 1API DPC++ code. You can even do sampling and see exactly what time was spent in which file and which line. You can see the execution of level 0 calls and the calls on the GPU. You can do this on an Intel Tiger Lake laptop, 12th Gen 12, 11th generation, or a DG1 system. What about other platforms? Well, I should just say that Intel has been very good about maintaining compatibility, and if something works on 9th generation, it will likely work on 11th generation, and you can try that on the Intel Dev Cloud and try these tools there. Here is an example with OpenCL with MPI, and you can see Intel 1API with MPI ranks running where the kernels are executing on the GPU. This is on AMD GPUs with Rock Tracer. You can see in Vampire Trace Visualizer exactly which kernel execution took place on which GPU along a timeline. We also ship a trace visualizer called Jump Shot with tau. It comes from Argonne National Labs, and we are very grateful to them for allowing us to ship it with the tau distribution. So you already have a trace visualizer that is bundled, but we also have support for the Chrome browser. You heard about the Chrome browser with flame graphs earlier today, and you can generate such visualization with the Chrome browser or Perfetto. This is the perfetto.dev, where we saw earlier today about you can just go to perfetto.dev, take this JSON file or compressed JSON file generated by tau, and then just load it and view the flame graphs over there and see the CUDA events and mapping. Vampire is the visualizer of choice. It's a commercial trace visualizer from TU Dresden. And if you say tau trace is 1 and OTF is the format for the traces, it will just generate the OTF2 traces which do not require any merge or conversion. Right after your application finishes execution, you can launch Vampire and view the data. And with Cocos, you can see the kernels executing. Cocos, as you may know, provides a way for you to use the Lambda functions to express parallelism in the code, but it also has annotations where you can do the push region, pop region, you can do a Cocos parallel for, and the first argument of these parallel for or parallel scan operations can be a user annotation so that you don't get gnarly template names, but the actual name that makes sense to you, and that name ripples into the tau with the Cocos profiling API, and all the profiling and tracing tools will show you that information, and the push pop get mapped to phases in your code where you can see the full flat profile under a phase. And you can see that in a node window in Paraprof, and you can even slice through the full runtime. You can see what events are happening in CUDA, what's happening in Cocos, what's happening in MPI, expand those, even take samples within that, and get a full view of what's happening in the application. Here are CUDA events executing on the GPU, and we also have mapping with PETC mapped to perf stubs, where perf stubs maps to tau. So you can see those PETC start-stop timer names all appear in tau profiles, neatly like this, with no change to the binary. This is a relatively new thing, and you will see more usage of this with ATPESC over time. But we have a number of runtimes that we support, whether it's MPI, OpenMP, OpenACC, ROCm, CUDA, and the best part is you can mix and match these runtimes. So you can say, I have MPI with CUDA, enable this configuration and launch tau exec that way, like this. And here you can see how app run is used with tau exec. And an example of OpenMP target offload support in tau, where you can see the kernel execution name, you can see the OpenMP name mapped right back to the source code, and exactly what the launch commands of GPU runtimes look like. So we have support for OMPT. Here is some information about an update on the AMD GPUs. It will run on Crusher and other systems. And I'll not go and spend time with PDT. It's a static analysis toolkit that allows you to source instrument your code. But with the source instrumentation, you must use the tau compiler scripts. And you can pick the make file like that and then set the variables. You can even set compile time variables like this, like tau options, and specify selective instrumentation or filter files which says instrument this, don't instrument that. And then you can even re-instrument your code based on throttled functions and reduce the overhead, make it more compact. You can use a number of these runtime variables like I already showed you with tau call site, where you can say, I want to track the load on the system. I want to track the power, or look at generating the trace files or call site profiles, and even memory instrumentation. Here are a bunch of memory environment variables. I don't have time to cover all of this, but let me just say that to install tau, to install HPC toolkit, to install NVHPC or ROCm or Intel One API, you can do it all with the extreme scale scientific software stack. This is a complete solution for installing your software. It comprises of using SPAC as the package manager to create a curated software distribution based on SPAC, and we can do this for bare metal installs as well as containerized images, as well as cloud-based images. Okay, and we also have virtual box support and cloud images. Starting from our first release in October 2018, where we had 24 products, now we have over 100 different products of HPC, as well as AI. We have support for PyTorch, TensorFlow in a container that targets a GPU. So you can target the MI250X, you can target the A100 GPU using a container. You can use SPAC to install the packages. This is how it looks. You just git clone it, turn on the environment, find the compilers and external packages, and then you can just say SPAC install tau, and that's it. It will install it. You can say SPAC, please install version 2.31.1 of tau, but with the GCC version 9.3. But turn on level 0 support, turn on OpenCL support for Intel, or turn on MPI support, but use MVAPICH2 version 2.3, which was compiled without wrapper RPath. If one does not exist, please install it. So you can give all of these commands. SPAC is a very versatile tool. You will learn more about it. I believe Todd Gamblin will be covering that. And containers. Just a show of hands, how many people here have not heard of containers? So everybody here knows about containers. Okay? So here is the difference between a type 1 hypervisor, a type 2 hypervisor which has an operating system, and containers which do not have a separate kernel. They use the kernel of the operating system and are more efficient for launching. You can nail down dependencies using a container, and we provide containers with E4S. You can see all of these Singularity images, Docker images, full-featured images, as well as base images. So you can build your own custom containers for AMD, NVIDIA, and Intel. And you can see base images for all of them. For NVIDIA, we also have support for x86, IBM Power 9, as well as ARM64 platforms. Here are 100 different products that come in a container. You can see all of these, including Tau and Trilinos, and you can just easily install the full-featured container on IBM or Intel platforms. And they have support for GPUs from AMD, NVIDIA. You even have support for languages like Julia. Maybe that's of interest to some of you as you're exploring that. And you can see with Intel One API that Cocos was installed with the SYCL variant, so it can handle the GPUs. We have a validation test suite, so we can check that these packages are actually doing what they are supposed to do. There's a number of images on Docker Hub. We even have an image on AWS, which you will use, by the way, to connect to Theta in the hands-on session. And we also have a project called E4S Container Launch Tool that can swap the MPI in your application that used MPI libraries from inside the E4S container with the system MPI. So you could use Intel MPI, you could use Open MPI, and do this swap at runtime. So you can distribute your code as a binary with the container. You can download Tau from here. This is where a lot of the development goes on in Eugene, Oregon. We have an active visitor program. If you are stuck, please feel free to come and visit us. We can arrange a visit, and it's a very nice place in the summer. I would like to thank our sponsors, including the US Department of Energy, Argonne National Labs, ECP, Berkeley Lab, Lawrence Livermore National Labs, Los Alamos, Sandia, PNNL, Oak Ridge National Labs, DoD, NSF, NASA, CEA, and our partners at other institutions for their support and the exascale computing project.
Anyone has a question to Samir?
Yes.
Hey there. Is it possible to sample that?
Is it possible to sample an application running in a container? That's correct. Yes, it is. And you can do that, and it will generate good profile data that will point you to where the application is spending its time. So yes, you can certainly do that. Yes. Other questions? Yes?
Okay, one more.
So if you're using the Tau Python,
Yes.
say you wrote like some code, C code wrapped in Python, you use a shared library. Can it, when it's running through Python, look at the shared library and profile?
That's a very good question. What it can do with Tau Python is, first of all, you'll get entry exits in Python, and then you will get the entry exits into the boundary of Python calling C. So if there was a function in C that Python called, it will show you the entry exit at the point where it's getting called. And then with event-based sampling, you can then use that crowbar to open up the C library and get a whole bunch of samples inside the library as well. So you can get sampling along with direct entry exit where the Python C boundary layer exists. You can get those events. Okay. Yes, John?
Why do you have a separate Tau Python instead of just Tau exec?
Because there are some complexities in Python wrapping, and we have tried to encapsulate all of that away by creating this Tau Python tool that creates the wrappers on the fly and then starts the execution. So we wanted to differentiate between Tau exec and Tau Python for that, for historical reasons.
I see. So you're using wrapping in Python rather than using the Python.
So we are using the Python interface, but to instantiate the Tau library within Python, it's a lot more complicated than just the LD preload that we do in Tau exec. That's why we have this Tau Python.
I see. We have a strategy. It's not released, so I probably shouldn't talk about it. But we call Tau Python HPC run.
Okay, very good to hear that.
Okay, thank you, Samir.